Another context in which we can use the tools of calculus to understand something about the graph of a function is if we ask about the long run of a function, or what happens in the long run. So for example, if we have a function that gives us the altitude of a satellite in miles after t hours, we could ask this question: in the long run, what is the altitude of the satellite? Well, what is this phrase, in the long run, really asking? This means after a long time, but what does a long time mean? Really, what a long time means is so long that any sort of peculiar behavior that is going to happen is in the past, and so that the only thing left is just sort of the long-term trend. So long that it's hard to be precise about what this means. So long that only the general trend is left. That's still not very precise. But let's look at the graph of this function to see what we might mean in terms of the graph when we say something like after a long time or in the long run. Well, here's a graph of this function. And so you can see that, so the t-axis is the horizontal axis. And when we say what is the altitude of the satellite in the long run, well, a long time in the future is far to the right on this graph. And you can see that if we just wait for a long time, eventually the height of this graph gets very, very close to 100. Now, it's not exactly 100, it turns out, but it gets very, very close. In fact, in this situation, we would describe this horizontal line at altitude 100 as a horizontal asymptote. So I guess what we really mean in terms of the graph in this long run is, what we're really asking for is there a horizontal asymptote to the right? And the way to attack that problem with the sort of cloud of ideas surrounding calculus is to take a limit, right? When we say to the right, you sort of get the question of how far to the right. And the idea is that we want to go infinitely far to the right. So what we really want to do is take a limit as t heads towards positive infinity of a of t, right? So if anything weird happens at some finite t value, well, since t is going to infinity, we're going to go past that unusual behavior and just see sort of what value it is that this limit zeroes in on in the long term. So to actually calculate this kind of limit, we'll need to come up with some tools, and the sort of tool you use really depends on what kind of function you're taking a limit of as t goes to infinity. So for this particular function, 100 minus 100e to the minus 1 over 4t, we can just think about the general trend of what happens as t gets very large. So I describe that as sort of plugging in infinity. And I've put quotes around the phrase plugging in because we aren't actually plugging in infinity. We're just thinking about the general trend of what happens to this function. But I will write it as if I'm plugging in infinity, but I'm never actually plugging in infinity. So when t goes to infinity, right, t is getting very large. So we're getting 100 minus 100e to the minus 1 over 4 times t, and t is a big positive number here. Okay, and as we write this, we have to keep in mind that it's not just any old big positive number. T is actually getting bigger and bigger and going off towards infinity. So when I write big, it's actually bigger than any particular number you might dream up. And I'm writing the plus because just to keep track of the fact that we're going to plus infinity and not minus infinity. All right. Now we can start calculating with this plus big, as long as we keep in mind that it's a number that's so big that it's bigger than anything in particular. So if we have a big positive number and we multiply it by minus 1 over 4, well, 1 over 4 times a big number is still really big, right? This big is so big that dividing it by 4 is still huge. So we're getting negative a very large number. So that gives us minus big. Okay, now if we raise e to a very large negative power, what's the general trend there? And again, we have to think about the general trend as the exponent gets more and more negative, so negative and bigger off to the left on the real number line. Well, if you raise e to a larger and larger negative power, the result gets closer and closer to 0. And in the limit, it actually reaches 0. So, right, it never actually reaches 0 for a finite negative power, but we're taking a limit as this exponent goes to infinity. And the idea is, right, here's a graph of e to the x, right? We're headed out this way on the graph. The idea is, no matter how close you want to get to 0, there's some point far enough out on the graph where the graph is closer to 0 than that distance you chose. And that is true no matter how close we want to get to 0. If we want to get this close to 0, well, we just have to go further out on the graph, out to here, say. And then the graph is that close to 0. You can see that no matter how close to 0 we want to get, all we have to do is go far enough out that way. And that's what I mean when I say that in the limit, e to a large negative power is 0. All right, so now we've calculated the limit. Now there's just some arithmetic to do. 100 times 0 is 0, and then 100 minus that is 100. So in the long term, this altitude of the satellite is actually 100 meters, or miles, I forget if I said miles or kilometers, above the surface of the Earth, which barely counts as being in space, I think. All right, so for another example of this sort of thinking about the general trend idea, let's take the limit as x goes to infinity of tangent of x. Now, this idea of just thinking about the general trend, it really only works for functions that are simple enough that we have some immediate understanding of what they look like or what they do in the long term. And tangent looks like this. And then it has these vertical asymptotes, and then it repeats like this. Okay, so as we go out to the right on the x-axis, so we're heading out towards plus infinity, which is in some sense all the way to the right, we have to ask ourselves, is there any single real number that this graph is sort of crowding around as we move to the right? You might want to say, because of symmetry, you might want to say, well, there's as much above the x-axis as below on this graph, so maybe the limit should be 0. But remember, whatever you think the limit should be, you have to ask yourself, can I force, by going far enough to the right, can I force the graph to stay this close to 0? Well, no, no matter how close to 0 you insist on being, the graph of the function, this function tangent, is going to leave the sort of close enough zone. And so that means that 0 can't be the limit, because the graph just doesn't stay close enough, no matter how far out to the right you go, because this is periodic. It's always, the graph of tangent is always sort of peaking up outside of this red band here, every pi or so. You might suggest, well, maybe that means the limit is somewhere else, maybe up here or maybe down here, but no matter where you think the limit might be, remember, for the limit to exist, it has to be possible to go far enough to the right so that the function stays in between, stays close enough to the limit value that we're suggesting. But you can see, no matter where you position this close enough band of values, the graph of tangent is going to periodically sweep outside of the close enough zone. And that means that none of these real numbers along the vertical axis count as the limit of tangent as x goes to infinity. And that means that this limit does not exist.